Okay, good morning, everyone. Today we have to start a subsection 1.2. Uh, this section, I don't think this is a hard section. This is something already you know, so I think I can go faster. We are, oh, sorry. Um, yeah, I, s- I change the setups, settings into the chat, then you can chat with me only. So let's start this. In this section, we have to discuss graphical and table methods, which we are using in descriptive statistics. Last time I told you what is descriptive and inferential statistics. Okay, descriptive is statistics, which means we are dealing with sample only. Okay, so graphs and tables we are using to interpret or simply show our results to others. uh, graphs um, graphs is the easiest way to show the results because thousands of or millions of data we can show within a simple graph. Okay, we will discuss these things later. And tables, normally if you consider a data set in general, you can see it's like a table. Okay, uh, then numerical summaries like mean, median, something like that. Okay. Okay. If you consider a graph, you know what is a graph, right? There are many types of graphs like bar chart, histogram, pie charts. Okay. So using this kind of graphs, a graph is like a picture. Okay, give us a precise idea about our data set. So these graphs can organize very clear way and display that we can understand really. We can understand what is going on here. What is this data set? Okay. Simply, we can summarize our data set by using a graph. Okay. Uh, these are the common method that we can use to show our output to others by using frequency tables, tally sheets. Normally, we don't use in these days. Histogram, stem and leaf plots, dot plots, pie charts, and scatter plots. In this section, I think we discuss this. I'll show you what is frequency table, histogram, stem left plot, stem and leaf plots. Normally, we call this leaf plot. Okay. Uh, dot plots, yes. Pie chart and scatter plots, we don't talk in this section. Okay. Okay. Uh, I think you remember what's a variable. Okay. Variable is some kind of a storage, right? So there are two types of this variable: quantitative and qualitative. Quantitative mean those are numerical values. Okay, that variable, if particular variable is a quantitative variable, which mean it has a values like my x, it has values 1, 2, 3, something like that. Okay, qualitative mean it is like groups or classifications, the non-numerical data, like okay, y is eye colors. Eye colors are like blue, oh sorry, blue, black, right? Those are non-numerical data. Clear? So quantitative, numerical data; qualitative, non-numerical data. Okay. So variable can be quantitative, either quantitative or qualitative. Okay. But we can deal with these two without any problem. Okay. If we want, we can convert our quantitative data, qualitative data to quantitative data, something like that. Okay. It's our choice. Then quantitative data, which mean numerical data, we can divide into two pieces. Actually, I have already uploaded these notes into a Blackboard. Okay, inside the material course materials, you can find these PDF files. Okay. Okay. Quantitative variables we can divide into two subgroups: discrete and continuous. So do I have a chat? Let me no. Uh, Let me check the chat. No, sorry. Uh, so discrete mean we can these all these values we can show. It's like integers, counting numbers. Those are discrete. Discrete can be finite numbers, or those can be like we can listed in an infinite sequence. Okay, like counting numbers 1 to infinity, something like that. But all numbers are like full numbers 1, 2, 3, 4, right? So those numbers we call discrete. Okay, and continuous mean values that we cannot, all values we cannot show within that range. For an example, values in range 1 and yes, my point. 1 and 2. Okay, within this in this range we cannot show all the values like 1.1, 1.2, 1.115. Clear? We cannot show all the values 1.99999. Clear? So these kind of values we call continuous values. So quantitative variable can be either discrete or continuous. Okay, but we can deal with these as well. Clear? uh, so if we consider a variable, we can talk about its distribution, how it is distributed. Okay, so it tells how about its values. Like for an example, if we consider a distribution of x, simply I'll consider my small set 1, 2, 3. So if I consider distribution is 1, 2, 3, you can draw it in like this is simple x. These are the values 1, 1, 2, 3, right? It's just one variable, 1D, one dimension variable. Okay. Uh, so it doesn't matter. It's, variable can be either quantitative or qualitative. So already we have our distribution, quantitative or qualitative. Okay. Quantitative case, normally it considers values. Qualitative is it considers either count or proportion. Okay, you will see what is this. So first one, if you remember, frequency table in the showing list. Frequency mean it's like a proportion. Okay, it's like a proportion. Number of times take from the total, something like that. So frequency, normally we don't use frequency. We, instead of that, we use relative frequency related to something. So frequency related to total frequency, that's we call relative frequency. Okay, so relative frequency of any variable, frequency, which means number of occurrences, divided by total number of observations. So let's say this one, let's say my y is the entire data set. Okay, so this is gonna be 1, 2, 3, 4, 5, and my x is 1 and 2 only. Okay, so relative frequency of this x, you can see, this is a simple example. Okay, so relative frequency of x, you can write how many occurrences in my x? 2. Don't consider the values. Okay, 2. 2 occurrences. So 2 divided by total number of occurrences. So total number of occurrences are 5. Clear? Okay. So this is the, don't confuse with this. This is the full set. This is the entire set. Okay. Y lives inside X. Clear? Okay. It is how I mentioned this. So what is going on? Sorry for that. This is my Y and this is my X. Clear? Something like that. So total number of occurrences are 5. So your relative frequency is 2 out of 5. Clear? Okay. You already know that. Okay. Histograms.
Hello.
There are 2 types of histograms that we are using for quantitative variables and qualitative variables. Those are very similar, but there is a small difference.
Hello.
For the quantitative case, for the quantitative variables, normally we use histogram. Okay.
Professor.
Main thing is histogram. You already know what is histogram. It is histogram is something like this. Okay. So its height of that bar gives us the frequency of that particular value. Okay. And the width of this bar, it gives the interval or range. Main feature is in histogram, bars, all bars are connected to each other. Okay, there are no gaps in between bars. Clear? That's the main feature. So height mentioned the frequency. So width, it shows us the specific range, okay, or specific value. So you know how to draw the histogram, but first thing is you have to divide your data set, you have to divide your data range into equal pieces before you draw the histogram. Okay, then calculate their heights or calculate their frequencies, then draw it. Okay, that's the main thing. But I would say like it is better if you can name the axis. What is this axis? What is this vertical axis? Okay, number them and also name them. Okay, that's the proper way to draw a histogram. You can see in this picture, bars are connected to each other, height shows the frequency, and they have named the axis as well. Okay, color, it doesn't matter. Okay, so this is how we draw a histogram for quantitative data. Okay, clear? Okay. When we go to the qualitative data, it is a little bit different. For the qualitative data, those are non-numerical. We use bar charts. I mean, it's a kind of histogram, but bar chart, the difference is in between bars, now we have small gaps. Okay, equal gaps between each bar. Clear? Others are same. First, you need to identify what are the categories, then measure their frequencies, which mean heights, then plot it. Bars do not touch. That's the important thing. Bar chart, bars do not touch. Okay, they have a small gap. So, right? So consider this example, days, Monday, Wednesday, Tuesday. Those are non-numerical data. So they have numbers, they have values, which mean frequencies for each day. So you can simply draw this using a bar chart. Okay, see, there is a gap in between each bars. This is not a histogram. Okay, that's the difference between how we show the histogram for quantitative and qualitative data. Okay, others are same. You have to mention, you have to name the axis. something like that. Okay. Stem and leaf plot. Stem leaf plot, it is some kind of very basic plot type which we are using. It is sometimes very hard to mention if we have a huge data set. So if we have a small data set, then it is easy to show our data by using stem leaf plot. Okay. uh, Sorry, how do we make a stem leaf plot? First thing is you have to sort your data into ascending order. Okay. Ascending order from lowest to highest. That's the important thing, and that's the first step. Okay. You have to do that, otherwise it goes wrong. Then you have to separate stem and leaf like this. This is stem part and this is leaf part. Okay, something like that. There are two columns, only two columns. So always only one digit, okay, only one digit goes to the leaf part. All other digits goes to the stem part. So for an example, if I consider 12, okay, last digit, which means 2. Oh, sorry. Which means 2. I'm so sorry. I think this laptop, I haven't installed the drivers. That's the problem. So 2 goes to the leaf. Okay. 1 goes to the stem. Clear? If you have three-digit number like 152, always last digit goes to the leaf. Okay, so 2 goes to the leaf. So 1. So 1 and 5 goes to the stem part and 2 goes to the leaf part. Okay, those two are two separate examples. Okay, those two 12 and 152, those are two examples. Okay, don't confuse with that. So if you have two-digit number, last digit always goes to the leaf and first digit goes to the stem. Yes. In general, decimal we don't mention, we don't show by using this stem plot.
So there was a problem on homework that required us to do a stem leaf plot for a bunch of numbers that have like 6.1, 7.2.
To do that, you can. There are few things we can do, but simply we can do like if we have only one decimal, we can simply multiply it by 10 and do it. Okay, something like that. There are few things we can use, but in general, no, we don't use stem leaf plot to show the decimal. That's the basic thing, but we can use. Okay, I think I have a note. I think I prepared a specific note for decimal cases. So I'll share it with you. Okay, because we don't have that in our syllabus. Okay, so I'll definitely share it with you today, maybe tomorrow. Okay, because yeah, I saw a few homeworks, a few homework problems with decimal, because those are not my homeworks. Our professor created that. So okay. Yeah. Okay, I'll just use this and tell you what's going on here. Okay, always last digit goes to the leaf part and the other digits. If it is a 3 decimal number, last digit goes to the leaf and the other two goes to the stem. Okay, so like that, the first one is standard one, you can simply mention last digit. It doesn't matter if that number already there, you have to repeat that number as well. Okay, but inside the leaf, all numbers, all rows are sorted. Okay, by ascending order. Clear? See, 0, 3, 5. 0, 0, 0, 2, 3, 3, 5 sorted. Okay, and also along this stem from top to bottom sorted. Okay, clear? If you have so many numbers inside the leaf, you can divide that particular row into two pieces like this split case. See, number two, the second row, there are so many 2 and 3, there are so many values, so you can split those two rows into two pieces. Like, see, one, there are two numbers in the leaf, sorry, in the stem part, 0 to 5 and then 5 to 9, something like that. Clear? It's not necessary, but if you feel like that is weird, then you can do this. Okay, clear? Next one is dot plots. Dot plots, it is better if you have a small number of data set. Okay, because dot plot, it is like it has only one axis. uh, it has values, your 1, 2, 3, whatever. Sorry, on top of this axis you mention frequencies. Okay, so I think in this just consider this data set. Okay, I think it goes from 20 something to 70. So there are so many numbers there, so you can simply mention this data set by using a dot plot like this. See, scale is start from 20, I think 22. Okay, 22 to 80. So all values in which below you have to mention in this axis. So all values in here, okay, all values measure, represent in this axis from 22 to 80, right? 23, 24, everything is there. Once you find a value, for an example, 22, go to the 22 and color above the value. Okay. Then again, sometime later, if you find another 22, then what you do? Draw a circle just above that, above the before uh, circle, before dot. Clear? That's how we have a stack of dots. For an example, 24, you have two values, which means there are 24 values. I don't I don't think I can find those two, but anyway, there are two occurrences. That's why we have two values. If you have three values, stack. Okay, draw a dot on top of the last one. Clear? Questions? This is only for a small data set. Okay, you can see it. If you have a huge data set, this is impossible. Okay. Okay, actually, why we are doing this? I mean, draw some kind of tables, plots. Actually, we want to see how this data set is behaving. Okay, how it looks like. That's the main idea behind why we are drawing these plots, tables, whatever. Okay, so first thing is overall pattern and its deviation. So deviation, it's always we have to talk, because each and every data set, it has some kind of deviation from its center, from selected point, something like that. You will see those things in few seconds later. Okay. Uh, so this overall pattern, simply we say let's say pattern. This pattern by it we consider this pattern by checking its shape, center, and spread. Okay. Uh, okay, I'll go to these shape, center, spread later. There is one thing I need to mention: outliers. Outlier mean if you consider a data set, sometime you will see that some values, those are very far away from uh, general data set. For an example, okay, it is a little bit hard to understand, but okay, if I have values like 2, okay, 2, then I start with 10, 10, 11, 12. Next one is 20. Okay, just consider these values. So once you check this, you will see first one is 2, and the next one is, next value is 10. Gap is about 8, right? Then you have 10, 11, 12. Gap is just one by one. After that, you will see 20, which means gap between 20 and 12 is 6. See, this is something like we call outliers. So our data set perfect, we have a perfect data set if we are considering 10 and 10, 11 and 12. Clear? But 2 and 20, those two values are far away from the general values. Okay, it is something like it's confusing, yes, because we don't have specific definition to outliers. How we identify, I mean, if you consider a data set, you cannot say this is outlier, this is outlier by checking by considering it definition. Okay, it depends on the data set, and we do a few calculations to identify is this value is a outlier or not. Okay, but idea is this values far away from its general values. Okay, clear? I think you have, yes, you have a section to find outliers. Yes. Once I go to the next section 1.3, you have quartile. Then at that point, I'll show you one method how we find outliers. Okay, by using quartiles, we can find outliers. Okay, outliers. Yes, it's a deviation. Data far away from the data set. Because of this, the problem of this outlier is it changed the shape of the data set, and it changed the average of the data set. I mean, average value of the data set, something like that. Okay, outliers, uh, it matters definitely. Yes, it affect it affects so many things. If we just forget about it, okay, if we just forget about it, it matters. I mean, it sometimes destroy our whole picture. Clear? So we have to deal with that, but 100% we cannot do that, but we try to do it, like at least as much as we can. We try to avoid outliers. Clear? Okay. We don't have example for outliers. Anyway, shape, normally we measure shapes by checking by counting how many peaks that we have in our data set. uh, and also we can check symmetricity or skewness. So I'll tell you what are these. uh, Symmetricity mean symmetric about the axis. Okay, I think you have seen when you are dealing with derivatives, those stuff, symmetric about axis, something like that. So if we have a graph, let's say this is my axis, and let's say we have one peak. Okay, just example, and this I'm telling you, okay, this is symmetric about this axis. Okay, Don't worry about the shape. Let's say symmetric about this dotted line. Okay. So skewness mean if this shape, if this peak shift to one side, we call it skewed. Okay, this peak shift to one side. Okay, not everything. I mean, only peak goes to this side or this side. Then we call skewed. There are a few pictures in this slide, so I'll show you that. Clear? So by using this, we can see what is the shape of this. Simply we call distribution. Shape of the distribution. Okay. So number of peaks, modality, normally we consider number of peaks. So if we have one peak, we call unimodal. If we have two peaks, bimodal, which means two bumps. Okay. If we have more than two, we call multimodal. It can be 3, 4, whatever. Okay. Like bumps. Okay. This is a unimodal distribution. As I mentioned, see, its peak shift into you can see its right hand side. Okay, so this is what we call skewed distribution. Okay, unimodal skewed distribution. How we tell whether it is left or right? I'll tell you. Okay, so this is a bimodal. We have two peaks. Yeah. Okay, symmetric distribution, which means we have a perfect symmetric shape. Okay, it doesn't matter. We don't need this kind of peak. Let's say we have x equal 1. That line, sorry, not x equal 1, y equals 1. So let's say this one. If you have x-axis and y-axis, y equals 1. What's the y equals 1 line? Oh, sorry. This one, right? Y equals 1. So see, it is symmetric. Okay, forget about the peaks. It is symmetric, right? If you consider somewhere here about this axis, this dotted line, it is symmetric, something like that. Okay, symmetric case. Skewness. If we have a symmetric distribution between unimodal with one peak, and I'm going to draw a right skewed one. Okay, its peak shift to a side, so we consider whether it is positive or negative by checking the side of its tail. Okay, its tail, its tail side. If it is a right, we call it right skewed. If tail is in the in here, you can see it is in right side, right hand side. That's why we call this right skewed. So right skewed, we can mention positively skewed. You can use those both words, either positive or right skewed. Okay, I use left and right skewness. Okay, but doesn't matter. Positive mean right skewed. Why right? Because its tail, the side of the tail is right hand side. Clear? If it's the left hand side, that tail, it's like this, then we call it left skewed, or in your words, negative skewed. Okay, clear? Because in general, right hand side we denote by positive. That's the case. Okay, clear? Okay, see this one, the right hand side one, we have a symmetric distribution. Whatever in this mode, median, mean, I'll tell you later. Okay, in chapter 1.3 we have to discuss these things. So anyway, symmetric distribution, which means about axis it is symmetric. Okay, negatively skewed or left is skewed, which means it has a tail in your left hand side. So why this first one, mean, less than, median, less than, something like that? Sorry. or in this case, mode equal median equal mean. I'll tell you later. Okay. If you consider, if you have a symmetric distribution like this, always mean, median, and mode, they are in the same line, which means they have same value. We'll see that later. Okay. Uh, okay. How we identify whether our data set is skewed or not. For an example, if you have uh, just for a moment talking about first one, consider second one and third one. Second one, when you see it, you know, okay, it is a symmetric one. Okay, it's clear, right? Last one, it is a what? Skewed one. You can see it. Third one, it's skewed because it has a long tail. Okay, one tail is longer than the other tail, left tail or right tail. In this case, it is right skewed, right? Third one. Okay, if you have stem leaf plot, how we say whether this is skewed or symmetric? Simply draw the shape. You don't have to do anything. Just draw the shape. Let me do that. I think I should be able to see. Draw the shape. Okay. It's a rough shape, but try to draw the shape. Then you can see it is um, so many data points goes to 4, 5, 6, 7, right? Which means it's skewed. Okay, skewed. Which side? When you turn it to this side, when you rotate it to this side, right? So you have a tail, long tail in your left hand side. Clear? If you turn it like this, you have this tail. So which means it is left tail, left is skewed or negative is skewed. Clear? This is the way. So online guys, can you see these slides?
Yes.
Okay, perfect. Okay. Measure of location. Location mean normally we use location to check the how we deviate from its center. Okay, it is like shifting. Okay, location parameter, we say normal parameter. We try to identify whether that data set is shift from its center. Okay. Location and variabilities. We need both measures when we are going to the distributions. You will see how this location and variability parameter are changing this your data set. Okay, so numerical description of a distribution. We need both location, which means how it deviates from its center, and variability. Okay, how this data set, how the shape shift this side, I mean not shift, how it shrink and how it goes like changes width. Okay. First, location measurements. Okay, measure of center. Measure of center, to measure the center, we normally use mean and median. Those are the center measurements. Okay, center mean let's say if you I don't know. Okay, so to measure the center, most common two measurements are mean and median. So mean, which means average. Okay, same thing. Mean and average mean same thing. How we do it? Get the sum of all values, divide by number of values. For an example, if you have values from 1 to 10, if you have values from 1 to 10, what you have, how do you find the mean sample? Just forget about that for a moment. How we find the mean? Summation of all values 1 plus 2 plus 3 plus up to 10 divide by number of instance or number of values. How many? 1, 2, 3, 10, right? Divide by 10. Okay. Normally you get the average. Same thing. Okay. Sample mean. Why sample? Because we are considering sample, right? Because if you remember last section 1.2, we talked about descriptive statistics. Okay. So we are dealing with sample. Since we are taking the measurement from the sample, this is sample mean. Okay, sample mean. So sample mean we denote by using a bar on top of the variable x bar, which means sample mean. Okay, so x bar means sample mean. If there is another thing, population mean, so we don't use this notation for that. It's a separate notation. So try to stick with that notation, x bar. Okay. Okay. So mean, as I mentioned, it's a location parameter. So that's the method we measure the balance of the data set. If you check this one, mean is somewhere here in this. I cannot show it. This one. This line is the mean of this data set. This line. Okay. This vertical line is the mean. So you cannot balance your data set if you pick first and second points. You cannot balance the data set. But if you place your object just below the mean, then it's a balance. Okay. It doesn't matter shape of the data set. Okay. It doesn't matter the shape of the data set. Like it can be skewed or symmetric. Doesn't matter. Okay.